Bound, an historical review algorithm derived from PAC bound that are interesting, what we call localized priors, and if I have time, I will finish with the transactive setting, which is not clear.
So are you sure that the micro is on? The one... okay, yes.
Okay. Okay, so let's start with definition. So I use the basic usual standard. So X, Y are description and label pair. We are supposing that, except stated differently, that all the data is given by an unknown distribution D. The learning sample are denoted by S. A predictor or a predictor and or an hypothesis is basically a function that starts from the description X and try to predict the correct label, and a learning algorithm is, I will stay there. A learning algorithm then is simply an algorithm that takes a training set and output a predictor. We have a loss function, the usual definition of loss function. The empirical loss is basically the average on the data, and the general loss is the expectation of the loss giving this unknown distribution D, right? So for PAC-based, we are interested in what we call majority vote classifier. What are they? It's simply you have a bunch of predictor, and they all have their opinion. Then you give some weight to each predictor, and the majority vote simply choose which one, which category has the most important votes. Here's the simplest case where the votes are either +1 and or -1. You have more general setting. That's not a problem. It's important to point out that many learning algorithms output majority vote, even if they are not considered as it is. Of course, all the ensemble method are of that way, but you can also see supervector machine as a majority vote, and the last layer of neural network as some kind of majority vote.
What's Q?
What?
What's Q?
Q? Q is the weight that you give to the voters. Okay, so we will call it the posterior. Okay, and so the risk of the majority vote, basically the probability that the majority vote make an error. So it's the probability that more than the half of the voter, given their weight, are misclassified. Okay, and the problem in PAC-based theory is we are interested in the risk of the majority vote, but it's difficult to have a bound on it, because it's based on the indicative function, which is not continuous. So we try, instead of bounding a related classifier that we call the Gibbs classifier. It's a stochastic classifier that basically for each example, choose according to the distribution Q a voter, and it is that voter that will decide. So the risk of the Gibbs classifier basically is the average risk of all the voters, right? And it is well known that there are a relation between the risk of the majority vote and the risk of the Gibbs classifier by a factor of 2. Basically, you can see it many different ways, but one interesting way to see it, it's a direct application of the Markov inequality. And so, and this is interesting because then you can say, well, I'm not happy with this factor of 2, because 2 times something that is not good is very bad. So there's a way to have a tighter upper bound of the majority vote, giving not only the Gibbs classifier, but what we call the disagreement also. And it is based on the Cantelli-Chebyshev inequality. So what you have is you can bound the risk bound by basically what we call the C-bound, that is basically based on the risk of the Gibbs classifier and also the second moment of the loss function, basically. And what you can see here This is the risk of the Gibbs classifier, and so you can see that you have more room where you can have a good generalization error for the majority vote. Sorry, because here, if it's darker, then the risk of the majority vote is very good. So you see that even if you have risk very, very bad, around 0.4, there are some way to have a risk of majority vote almost zero there. So it's a tighter way to bound the situation, but I won't go into this today because we'll need more than 1 hour to talk. Now some PAC Bayesian bounds, so a bit of pre-story of everything started in 1975, even if the people who were working on that didn't know a thing about machine learning. It's about variational and the other theories. So here is what we call the Donsker-Paradigm inequality. It's something that relates some kind of an expectation on a distribution P to an expectation on a distribution Q. And the relation between them is quantified by the Kilbert-Leibler divergence, which is defined as in this slide, right? And this is the most important part of the PAC-based approach. It helps us to transform something that we have a priori, because before seeing the data, we don't have a clue how to do the majority vote. So we have to define a prior, which is a distribution on the voters, that you have to decide only by your previous knowledge of the problem, not using the data. And then you look at the data and you say, well, my P is not so good, so I would like to change the weight of the voters in order to have a better performance on my data. And you can do that, but there's a price to pay, and it is basically the Kilbert-Leibler divergence. After the prehistory, you have John Chartiller and Bob Williamson. John will talk this afternoon. That were the first to really think about PAC analysis, not probably approximately correct analysis of Bayesian estimator. And after that comes David McAllister that give the first bound on known as PAC-based bound, and it's basically the following. Okay, if you look at it, you have what you have. That's first you have a PAC bound, so the probability will hold almost all the time. Okay, and what is the bound is saying? It's basically saying first that for any distribution Q that you want to find, okay, the bound is uniformly valid for any majority vote that you will like to consider. For any majority vote, the difference between the true generalization error of the Gibbs and what you see on the data is always bounded by basically the difference between what you think a priori of what should be your majority vote and what you decide to be your majority vote, and a complexity term that is not so big, basically. Okay, and all the PAC-based bounds are basically in that form. But in the case of McAllister, it's quite easy to isolate the risk, and you can see that you have a convergence on 1 over square root of m, which is basically what you intend. A few years after, Seeger and then Langford, and in fact, they were discussing together, so I will call this bound the Langford-Seeger bound, arrived with a more tight bound, which is based on what we call the small KL. The small Kilbert-Leibler divergence is simply the Kilbert-Leibler divergence between Bernoulli distribution, the first one having a probability of success of Q, and the second one having a probability of success of P. And so here is the formula. And so you have a distance again between what you observe on the data and what you would really like to minimize. And it's always depending on how far you have to change what you think a priori and a term, right? So And here is basically how it works. Okay, supposing that this term is 0.6. Okay, and supposing that you empirical risk observed is 0.1, then you have this Kilbat-Leibler, small Kilbat-Leibler value distribution that gives you this curve, and you have the two bounds, which is integer and superior. And I will show you basically how it works in general. So above all, the bound in PAC-based theory are basically can be proved with basically the same ideas. I will show you the important step of that, and then you will be able to understand that if you want to make some other change to your PAC-based theory, then I will show you how you can manage to change basically the step of the proof in order to adapt to different framework. Okay. So the idea is, in general, if you have a convex function delta, then you will be able to have this kind of PAC-based bound, meaning that the distance corresponding to delta between what you observe and what is the true generalization error of the Gibbs risk is always bounded by the Kilbat-Leibler plus some complexity term. In general, the complexity term is basically the sum of all the binomial times an exponential, and you have to make some supremum on all the possible risks that you can observe. So how it works? I tell you the first step is the change of measure inequality, that the Dancer-Baradan inequality. No, this is an important stone for the proof. But you also need to have a PAC, a probability approximatively correct bound. So you need some kind of inequality. Here we will make use of Markov inequality, but we can think about using other type of inequality. And also, this is not necessarily because you can have other inequality concentration, but here I will use the idea that the empirical risk on a finite set of n element can only take n plus 1 values. Okay, so the empirical loss in general. Okay, and so how you prove the theorem? So you start from the left side of the inequality, and then you say delta is supposed to be convex. So I can use Jensen inequality to get the expectation outside of the function. Of course, we have an inequality here. Then you use Dancer-Baradan or any change of measure inequality that make your KL appear. At that moment, this is always true. There's no probability here. Whereas the PAC bound appearing is when we make use of Markov inequality. And then what you do is the fact that the prior has been seen before seeing the data means that you can swap the two expectations on certain measurability condition I won't talk about. And then you think about the fact that there is only n plus 1 possible value for the expected empirical loss, and so you make some stratification of that, and then you say, well, the worst case is when among all the possible risks, I will take the worst case, and it is the end of the proof, right? Yes.
Can you please just give the reference for this?
I can send you my slide if you want. But yeah, the reference is the thesis of Pascal and some other paper.
AX that 2016?
Yeah, I think it's the first time that we had this. But I will be pleased to send you my slide if you want.
So when you apply the Jensen inequality, do you assume convexity in both the arguments simultaneously?
See?
When you apply the Jensen's inequality, do you assume that the function delta is convex in both the arguments?
Exactly.
That's why you can...
Yeah. So it's convex on both. Yeah, it has to be.
Can you repeat the question before answering?
Okay, so the question was, my assumption about delta is to be convex on both arguments. not only on one at a time, right? Otherwise, this was not be true, right? Okay, and so what we have then, if you can then simply have recover the Langford-Seeger theorem. Simply, you have to say the delta function is the small KL, and you can retrieve McAllister simply by saying that the delta function is 2 times q minus p to the square. You can retrieve the Cattani bound. I suppose Cattani will present it a bit. I will have a chance to present it. Simply by taking, this is an interesting one. The idea is the following. You want to have something convex, but that is linear on Q. And you want to have a 1 here. And so you make a bit of calculation, and then this is the nice function that you obtain, which is convex, okay? And which gives you this Cattani bound. Also, the Cattani bound is very interesting because it's the first one that has a convergence rate of 1 over n. But it's not exactly true because there are some kind of bias here. Okay, but you can control the bias. You can take a very small c and things like that. But nevertheless, it's interesting. And Olivier has some interesting result also in statistics using PAC-based theory in order to say that we can manage to have fast rate. Are you going to talk about that this afternoon? No, that's too bad. Okay, and also we have the bound of Alki et al. That is, I won't get into, but we can also retrieve by our bound. And just to say, well, okay, I say that you just have, for the Seeger bound, you just have to use the small KL. Why this is so, and why do you have the 2 square root of n in red instead of this supremum of over r, blah blah blah, and blah blah blah. The idea is you can manage to make some easy calculation out of that. You simply say that, okay, this is the KL function, so you replace delta by KL, you make some mathematical manipulation. You say, well, the empirical risk has only m plus 1 possibility if the size of the training set is m, and so then you remove all the problem with the empirical risk. You are stuck with the true risk here, but what you can see here is the empirical risk follow a binomial law. So if you expand this binomial law, what you will see in this, you will appear risk to the k and 1 minus 3 to the m minus k that will cancel with those 2 1, and so everything cancel out, and you are obtaining something that is don't have to consider neither the risk nor the empirical risk. But it's not so beautiful. So you look at Maurer lemma, and you can make it much more small, interesting, basically. Okay, and of course, this is only true for IID situation. Otherwise, the empirical risk do not follow the binomial law, so you cannot do that. But the general theorem, nevertheless, is always true. The only problem is you have to deal with the calculation of this complex, the I of delta of m. That can be extremely awful if you are far from the IID situation. Okay, everything's fine now? So a bit of history. I start the prehistory of the Duncan-Varadan, then I talk about the Williamson and Schottler PAC analysis of Bayesian estimator. I tell you something about the McAllister bound, and I tell you something about the Seeger-Langford bound. So I will try to rapidly make an overview, partial overview of what happened in this field. And so you will have all the reference if you want to look at it after that. So in supervised learning, for example, there's a lot of application to linear classifier and in particular to S supervector machine. I will tell you something about it later on in the presentation. There's a lot of things about theory Of course, the Catoni is one of the most important paper to read, but it's a bit difficult. Maybe you should not start with it. But there's a lot of an interesting thing. But you have also Mir and Zhang. McAllister in 2013 has something that a PAC-based approach that explains dropout. German et al., for example, 2016 has an interesting paper with Francis and Simon Lacoche-Julien, I think, talking about the link that is that PAC-based allows us to go from frequencies approach to a Bayesian approach. So it's some kind of a bridge between those two realities that are not talking to each other too much. Also, you have Ben London, whose poster is exactly there, that has a poster in NIPS this year, that gives some interesting bound about anything that you can do with stochastic gradient descent, especially, I suppose, deep learning, which is what we always talk about these days. Also, you have this interesting thing that if you have a bound, you can try to minimize it, or to minimize the surrogate of it. And then you can construct many different algorithms that will, you know, that will have some nice property because they will be leaded, they will not be more, they will have some guarantee due to the bound. And we also have PAC-based theory and regression, stochastic learning. If I have time, I will give you some example about that. But also domain adaptation. Domain adaptation is something that is quite difficult to handle. So what we do with Germain and others, we try first to make a PAC-based bound and then try to minimize it. And so we can organize what we should do in such a situation. But you also have PAC-based bound on non-IIE data. This is more difficult because then you cannot do the usual thing, but there are some concentration inequality, namely Azuma Evding, and some generalization out of that can help you to deal with this ugly term that is I of subscript delta that I showed you. Of course, non-IID data includes U statistic of higher order, so it's quite interesting to be able to have such a bound. And last situation that I want to point out is the sample compression setting is the situation when the voters are defined on the data. So the voters are defined using the information contained in the training set. This is quite tricky because you cannot have a prior on something that you cannot have seen yet. But there's a way to do that, and you make a prior on all the possible way of constructing your voters and stuff like that, and you can have this interesting sample compression setting that it can be analyzed through PAC-based. So this is for the supervised learning. Density estimation also, we have an interesting result about that. Martingale, reinforcement learning. Oh, I forgot, for reinforcement learning is Joël Pinot et al. No, it's there. Okay, far there, Joël and Pinot that do something in the reinforcement learning. And there's a lot of other results, so I apologize for people who are not in this slide. Okay, rapidly, what can we do with algorithm derived from PAC-based bound? Okay, so here is the Olivier Catoni's bound. Okay, I showed you before. And what you can see, minimizing this bound is minimizing a trade-off between a certain constant to be defined between your empirical risk and the value of the Kilbat library. So you have a trade-off here. Okay, and then so minimizing the bound is minimizing this trade-off. So it's quite obvious that it's something that should be interesting to do. And of course, C will become an hyperparameter of your algorithm since you cannot really decide which is the best C depending on the data on which you will do it. And what is interesting is if you restrict your prior and your posterior to be Gaussian, isotropic Gaussian, then you end up with exactly the set covering, the super vector machine algorithm. So you rediscover SVM using that. In fact, it's not exactly SVM. You have to replace the hinge loss by the sigma ideal loss. But otherwise, it's about the same algorithm. So PAC-based give another justification to this nice algorithm that is SVM. But this is not only with SVM that we can have that. You have a PAC-based bound minimizer that can give you AdaBoost. In fact, it's AdaBoost regularized, and it's not L2 regularized, neither L1 regularized, it's KL regularized, which is exactly something in between. And so the theory says that you should regularize AdaBoost, but with the KL. You can have kernel regression. You have also a structural output algorithm. The one of Cortes and Mori, for example, is exactly the bound minimizer of a PAC-based bound on structural output, of course. But we also found a lot of new algorithms simply by defining new PAC-based bound and trying to minimize it. Of course, if you are in the IID case, in the classification case, you only retrieve something that has already been found, because there's a lot of people who did a lot of work on that. But if you go in other frameworks that are more difficult, this is the first way to go and to see what you should do. You try to find a PAC-based bound, and then you minimize it as your algorithm. Okay, localized prior now. If you look at this, you can see that the bound can be very awful if the KL is very, very big. Okay. So suppose that your prior is very bad, and then you are forced, in order to have good empirical performance, to really choose a Q that is very far from it. Then the bound can be very, very, very big. Okay. So the bound says that you have to make a trade-off between empirical accuracy and complexity, the complexity being represented by the KL. If you want to have a good generalization, basically. Okay, but there's a luckiness argument here. So it can happen that you cannot find a Q that can achieve the trade-off in a way that you are satisfied. So the question of a localized prior is, can we have some guarantee that 30 minutes, okay, not seconds, okay. Okay, so we have some kind of luckiness argument here, okay, and so we would like to have, is there some possibility to have some guarantee that even if we are not really lucky, then the bound will never be very, very big. Okay, I remember you that the KL can even be infinite, which is a very bad bound. That's exactly what I say. So one way to do that is to be sure that the prior is not bad. So you can reserve a part of your training data in order to learn the prior. And it does not have to be so big, because you don't want to have the best prior, you just want to have a prior that's not so bad. And then, if you do that, of course, you will improve your chance to have a good guarantees, right? But another way to do that is to make a prior that is distribution dependent. I recall you that the prior cannot be data dependent, but it can be distribution dependent, okay? But the distribution is an unknown. So if you do that, your prior will be unknown, okay? But this is not really a problem, because you don't need to know the prior P. You just need to estimate the Kilbat language divergence between this prior and your posterior Q. Okay, so this is a way to do that, okay? We have Shatter et al. That has proposed this. So they say, well, I'm working on Gaussian, and I will try to find the Gaussian that it will be in the center of the data, basically, which is a good idea. But where is the center of the data? You don't know it because you don't know the distribution, but when you observe the data, you can estimate where is the center, and you can bound the error that you are making. sense of that. Olivier Catoni has a lot of ideas like that. Yeah, in fact, it's the first one who really get into those ideas. We have also, with Guy Lever and John Chatero, I have some kind of result about that. I will just show you a bit. So what we decide is we take the following prior, which is a good idea of prior. Okay, I say, well, I will put more weight on voters that are good, which is very good, a good prior. Of course, I don't know the distribution, so I don't know the risk, so I don't know the prior. Okay, but this is my prior. Okay, and what we prove is if you take the following posterior, which is I will try to put more weight on voters that are good in my data. This Q I can calculate it. Okay, and then so can I have a possibility of calculating the kilowatt library between this P particular and this Q particular? And of course the answer is yes. And what is the idea? We apply a second base bound. This time, basically, it's a PAC base bound that will bound the kilowatt library difference between the specific P that we don't know and the specific Q that I showed you, right? And this is basically so here you have some time that you know that if you have enough example, you will not have, your true risk will not be so far away from your empirical risk, right? Because you don't have the kilowatt library divergence. Another way to do localized priors is simply to make the KL disappear, saying I don't need it anymore, I put it in the basket and I throw it away. So this is a bit of magic. I'm not sure I totally understand why it works, but the proof is there. Okay. So the idea is to consider auto-complemented voters. Okay. So if you have a voters in your set, you have a voters that is thinking exactly the opposite. And we will say that the posterior Q is aligned on P, okay, if basically the sum of the two auto-complemented voters according to Q is the same as the one according to P. Okay, for example, if you have exactly Q is equal to P is equal to the uniform, it's working. But so this is a big constraint. So this, for example, if you have 2n voters, means that each voters cannot go too far from P. For if P is the uniform, then the voters cannot have more than a weight of 1/n. And okay, because the average will be a 1/2n. So this is a quite good constraint, but it's not so bad because except for a very weird case where H is uncountable, you can always find a posterior that is aligned that gives exactly the same majority vote of any posterior. So you give your posterior, it is not aligned on P, I can manage to transform it into a new posterior Q prime that will be aligned on P. So for which I will have this nice property, okay? And when you do that, magic appear, the KL simply disappear. Wait, yes?
Sorry, what's BQ?
BQ is the majority vote, okay? According, you put Q is a distribution on the voters, and so it's a majority vote, but weighted by Q, okay? So here's the theorem. Again, it's exactly the same structure that I showed you for the general theorem. You do exactly the same thing, except here you change your change of measure inequality. The change of measure inequality that I will use, I will show you in the next slide. But for the rest, it's exactly the same proof. It's exactly the same step. I'm just changing the change of measure inequality. Right? Of course, why this change of measure inequality works? It's not always true, basically. It's true for when delta is equal to the small KL, and it's true also when you have the McAllister delta, so 2 times Q minus P to the square. It's not true for the Catanese bound, for example. Okay, you have to have delta has to have some kind of property, but for the two most important delta, it works. Here I will show you basically the idea of the proof. Okay, for the situation where we are supposing that we are doing with delta is equal to the McAllister one. Okay, and so you see, there's a lot of different ways to do that. You separate H, your set of voter, into two sets. The one that think in one direction and their complement. If it's an uncountable set, you have to take care about measurability and things like that, but I won't get into the detail. And then what you do is you take your expectation, which will give you your here. So you have this expectation. And so what you want to do is to transform it a bit. There's a mistake here. No, it's okay. No, there's a mistake. This is the P and this is the Q. But this is the idea. So I want to transform the expectation on P simply on the expectation on Q without having to pay the KL Kilbert library divergence. And the idea is the following. So you separate your classifier between the one and their complement. And so what you take is your expectation is the integral over the first set of class and plus the integral over the second set of class. Of course, you have to take care about measurability, but the idea is there. Okay, and then what you do is the following. You realize that if you change h by minus h everywhere, okay, then your integral is on this h1, okay. But what happened to the risk? But the risk of minus h is minus 1 minus the risk of h, and it's exactly the same for the true risk. Okay, so and you know that 1 minus 1 simplify, and you know that so what you have true risk minus empirical risk. But since you have a square, you can change it. Okay? Yes?
Why is that? The risk of minus h is 1 minus the risk of h?
Because they are auto-complement. Minus h think exactly the contrary of h. Okay. We are in the binary case where the voters can vote +1 or -1 only. So if you don't think minus, you think minus h. Okay. Good question. And so then you join your two integral, okay, and you know that you are in a situation where it is aligned. So the sum on P is equal to the sum on Q, and then you do exactly the same step but background, and you obtain what you want. So the change of measure inequality is free in the case where we are in aligned posterior, right? So that's why you obtain basically the trick of free. I have to point out that for the Gibbs, this is not really good. Since all the voters must be very close to the prior, the risk of the true Gibbs can be very bad if you have a lot of bad voters. Because if you have bad voters, their complement is also bad, even worse. Okay, and you have to. The best thing you can do is to give all the way to the less bad one, right? So for the Gibbs risk itself, it's not really something that will give you a bound that is interesting. It will be a tight bound, meaning that the difference between the empirical risk and the true risk will be close, but it will not be a good bound, basically, because empirically the Gibbs risk will be bad. Then you can think about what I said at the beginning of the talk and saying, well, instead of using the Markov inequality to have this factor of 2 between the majority vote and the Gibbs risk, you can try to intervene what I call the second moment, or the disagreement expectation between voters, and you have another kind of PAC-based approach that you can do and things like that. Yes?
Sorry, so I have a question about those aligned posteriors.
Yeah.
Would you have a constructive heuristics of such posteriors? Because I'm failing to see if I take any posterior, how to make it aligned with respect to
It's
the
very
environment.
easy. It's very easy. It's high school math.
But how would you do it? I mean, for example, if I take a cluster area which is exponential minus the empirical risk, would it be always aligned with the corresponding prior? I mean, wouldn't you have...
In fact, choose the posterior that you want. Don't care about being aligned, and I will show you how to align it. Okay. Basically, what you do is you give the voters that you don't want. You give them 1/n weight and 1/n weight, and so they cancel each other because they are opposite. They are complement. Okay, and then so you can manage to play with the weights. The problem that will give is an aligned posterior. If you have bad voters, you will end up that those voters will be bad in the average. So the Gibbs risk will not be good, but the majority vote risk can be good. And so we have some proof of theoretical and empirical proof that we can do that. And one of our algorithms, MinCQ, is exactly that. We are working with this aligned posterior stuff, and we have an ensemble method that beats basically SVM on many benchmark like MNIST and so on. So there is something there. It's not totally understood, even by me, but I think it's interesting. Yeah.
Does it go through the continuous case?
Yes, it goes to the continuous case, but there are some kind of exception. In the continuous case, you cannot always assure that any posterior Q can be reweight in an equivalent aligned posterior Q prime. There are a mild condition, but it's not a big condition. Yes?
Is there some price to pay for the alignment?
Yeah, I tell you that the Gibbs risk will be bad, because you have to give weight according to your prior to everybody. And if a posteriori you find out that those guys are bad, so if H is bad, minus H will be even worse. And you have to give to them basically the weight that you should give a priori. So for the Gibbs risk, you can end up with a very bad Gibbs risk empirically. So that's the reason why it's not a miracle.
In the majority vote, you still have some price, or?
For the majority vote, most of the time you have a very nice majority vote, meaning that it will be very small. But you don't have the guarantee through the PAC-based bond and the Gibbs risk, because the Gibbs risk is bad. And twice something bad is very bad, right? But you can do it by the C-bound that I showed you at the beginning of my talk, and you have some kind of better possibility of generalization there. Okay? So I have time for a transductive. So what is the transductive setting? Okay, the IID setting is simple. You have Mother Nature that gives you some example according to her distribution, that she is the only one to know it, D. Okay? And they give you your training set in this way. In the transductive net setting, there is no intervention of any goods at all. You have a lot of data, okay? S plus U. And so you take at random some part of your data. So let's say S. You ask to a human person to make the label out of those examples, and you want to infer to the unlabeled part that didn't been seen by your human being to be labeled by your algorithm, right? And so this is important. In probability, you always have to define what is your stochastic experiment. Here, the stochastic experiment is the action of choosing a subset of a big set of unlabeled data and label it, right? In IID situation, the experiment consists of asking to Mother Nature to give you your training set, right? And if you have a PAC-based bound or a PAC bound in general, that means that your probability is 1 minus delta over a lot of different redoing of this process. So the guarantee in transitive setting is the guarantee that if I start again with unlabeled data Z, that will not change. Z is the universe. Okay, but I ask for human people to label a different subset S. Then in the protocol, I should end up basically most of the time with what the bound will tell me with probability 1 minus delta. Right? Okay, and so here is the bound. Okay, so again you have a delta that is that should be convex, and then you have exactly the same structure of bound, except that the complexity term, the T on delta is a bit more complicated, right? But it's a bit more complicated, but it's a finite sum, so it can be calculated. And how can we prove it? But again, it's exactly the same pattern that you have. You start with your delta, you take the Jensen inequality, you take the change of measure, you take Markov inequality, you take the fact that the prior doesn't see the data, so you can swap, and then you have this idea that, well, now the empirical risk in this setting is not following a binomial law, it's following a hypergeometric law. So then I have to use the hypergeometric development, and this is why it's more ugly than in the IID term. It's okay. And what you can see also is, for example, people don't like KL divergence, for example, but then you have to change your change of measure. And there's a way to do that. There's a PAC-based theory that allows you to do stuff with really divergence, for example, and things like that. You have a lot of possibility, and basically it's always when you want to play, you play with one of those 6 steps. Okay, so I will stop here. Big thanks to Mario Marchand, my forever colleague in PAC-based theory. Thanks also for the Graal team, especially Pascal, a former Graal team that gave me a lot of those slides. And also thanks to John, Liva, David, Guy, Evgeny, Ilya, John, for a very nice talk during those years. And here are what you have to read if you like the packets.
Thanks, Francois. We have time for a few questions.
Thanks. Thank you very much for the great introduction. One thing that's confusing to me is concerns the role of the prior. If I understand correctly, it's the equivalent of the complexity measure that we usually have in normal PAC bounds.
Yes.
And how come, I come from normal Bayesian statistics, and here, the prior, its role is to favor hypotheses that we consider to be a priori more likely, and things that are not likely we penalize them. How come the prior seems to play such a low role in the final bound here? I don't know, it seems just surprising to me.
First, my prior is not on the model that I want. I'm not trying to find the model. This is a frequencies approach. I want to find a classifier that is of the form of the majority vote. This is the first step. So in the frequencies, more ideas, you have to, you can say, I don't want to make any a priori decision, and I can have a bound that is basically a flat bound. For example, the Occam-Razor approach. So you can have such a thing, because the idea is, if you have, the problem is you want to have a training set bound. A training set bound must be valid for any possible outcome, a priori, before seeing the data, right? So basically what you do is, you try your favorite testing set bound, for example, approximation by a normal or thing like that. And so what you try to do is, if you try one outcome, one majority vote on your test set, then you will have a probability of 1 minus delta of failing. But because of the union bound, if you go if you want to test 2 possible majority vote on the same testing set, to have an overall probability of 1 minus delta of not failing, each one has to have a probability of 1 minus delta over 2, for example, right? But what you can do, if you can say, I have two classifiers to check, okay? But I really think that the first one is the one that I want, and I will just check the second one just to be sure. So what you can do is you can say, well, I want to have a guarantee of 1 minus 2/3 delta for the one on which I believe, and 1 over 1/3 delta on the one which I believe less. And if I'm lucky, I will find out that the first one is the one that I want to keep, and I will have a better guarantee because the 1 minus 2/3 delta will be something that it will be better. It's about the same idea that is using here. And so the idea is, we believe that if we are close to if Q is equal to P, it's basically a testing set bound, okay, based on spatial concentration in inequality, right? But what you think is, well, I will stratify the penalty according to some kind of measure. And the measure is the Kullbass-Leibler divergence, basically. And why we use the Kullbass-Leibler divergence? It's because of the Danz-Curve-Aranon inequality that we have in hand. But there are other inequality on which you have different way. But it's always the same thing. The complexity in the PAC-based approach is given as how far you are from what you were taking a priori. That's why it's so close to the Bayesian approach. Yeah? Yes?
So I was wondering, so the concentration inequalities you showed are for the empirical risk, so that's a mean of a random variable. So in the book by Pascal Massard and Boucheron, they look at other functions of IID random variables. You can take their techniques for you can just plug that into the PAC-Bayesian approach and it will, it combines perfectly. But has anyone investigated that? Do you get,
I think Olivier did something about that. Est-ce que Pierre Alquier did something about that? Or
Slightly related.
slightly related?
PAC-Bayesian telegrams inequality or
Yeah. And also there are some, Evgeny did something with Bernstein inequality, trying to get more tight bounds and things like that. Yes, there's some kind of work on that direction. But yeah, I will look at Talagrand inequality. Maybe it's a good idea.
I have the feeling that you are choosing the prior and the posterior independently. So I don't know. I'm wondering if there is like a rule between them, or just
the prior has to be chosen before seeing the data. Okay, and the posterior has to be chosen after seeing the data. And so you try to find a posterior that gives a good majority vote. Okay, that has good performance on the data that you have observed. But if you choose a cube that is too specific on your data, then you will have a very bad KL divergence between your prior and your posterior, and you will pay the price for the generalization bound. So this is the PAC-based. There's a trade-off. You want to be good on your data, okay, you can, but it's a price if your posterior is too far from your prior. If you have a good prior, you are lucky, you can have a posterior that is very close to it. And then you will have a very good generalization bound. But if your prior is stuck, it's very bad, then you will not be able to have good generalization if you really want to have a good classifier at the end.
Okay, so there is no base rule between posterior and...
The base rule is not used here, okay, but it's not exactly true because there's a paper, I might give you the reference of Francis Bach, Pascal Germain, and Simon Lacoste-Julien, that try to explain what are a similarity between PAC-based and Bayesian, because there are, okay, but at the beginning, PAC-based is a frequencies approach, but with Bayesian ideas, right? So the maximum likelihood you can retrieve it and anything like that if you put your PAC-based approach in a correct way.
We have to move to the next speaker. Thanks again, François.